Xiong. Okay, sure. So, and also Xiong, he is now a graduate student in EPFL Switzerland. Okay, so let's first talk about what is this Finitary Random Interlacement. This is a random spatial process recently introduced by Louis Bowen. He's a mathematician in University of Texas at Austin, recently in 2019. He introduced this model basically like a tool to solve something called a Gaboriau-Lyon's problem, which he said is a measurable version of he said it's a very famous problem called the von Neumann-Days problem, but I have no idea what these problems are. So I only know this is a kind of a Poisson point process on the space of finite nearness neighbor trajectories. So intuitively speaking, we can think of this random Finitary random interlacement as a Poisson cloud of finite nearness neighbor trajectories. Each of them are distributed according to a geometrically killed random walks. So if we want to define this in precisely, then we can consider an intensity measure of a form like this. So here, this T stands for the average length of a geometrically killed random walk. And note that we have both this T on the average length of this geometrically killed random walk, and also we have a T plus 1 here in the denominator. Okay, so Finitary random interlacement at level U, denoted by FIU, and also, I'm sorry, here's a typo, we also have a T stand for the average fiber length. Okay, so this is a Poisson point process, or PPP, on the space of all those finite nearness neighbor trajectories with intensity measure as U times this nu times nu of T. Okay, so if we look at a Poisson point process like this, then we can say there is actually an intrinsic built-in trade-off mechanism within this Poisson point process, because we can say this T both on the average length of those killed random walk, but also on the denominator here. So this means as T increase, in average, we'll have a longer and longer passes. But if we look at every point, then emitted from this point, the number of trajectories starting from those points will be fewer and fewer. And so the trajectories will become more and more sparse. So there is a kind of a natural built-in, what should I say, natural built-in trade-off mechanism with respect to this average fiber length T. And as you can expect, as this T first, if we let it go to infinity, then what happens? If we look at every point as T goes to infinity, then we will have almost no trajectory starting from or ending at this fixed specific point. So all the trajectories we can say if we fix a local set, spatially a local set, then all the trajectory we can say traversing this set, they have to be something coming from far away, and then hit this set, traverse it, and then going to also somewhere far away. So this means as T increase, the Finitary random interlacement will look more and more similar to a model with trajectories coming from infinity and then going back to infinity, those double infinite trajectories. But on the other hand, if we have T go to 0, but at the same time let U go to infinity, but we keep the multiplication U times T to be a fixed number, we call it lambda, then it is not hard to prove that this Finitary random interlacement model will also converge to another very famous celebrated spatial process in stochastic geometry, stochastic physics, which is called the Bernoulli bound population. And we can also easily calculate the open probability for every h. This p is 1 minus exponential 2 times lambda, something like that. And back to the other hand, if we fix U and let T goes to infinity, the picture will be all the trajectories will come from infinity and then go back to infinity. And in this case, Bowen, back in 2019, he proved that as t goes to infinity with a fixed u, the finitary random interlacement will converge under the weak star topology, converge weakly to something called random interlacement, actually an infinite random interlacement with intensity equal to 2d times u. And this infinite version, this random interlacement, this thing was introduced by Alonso Schneemann from ETH back in 2010. His main motivation to introduce this infinite model is to study the local limit or the limit at a mesoscopic scale of a simple random walk restricted in a large torus. So the main property proved for the infinite version of random interlacement are as follows. They look at the vacant set, that means the set not touched by the infinite version of the random interlacement, and they prove that there is a critical value u star such that for all u less than u star, then the infinite version of random interlacement, its vacant site, its complement will percolate. That means it will have a unique infinite connected component, collected cluster. And when for all u greater than this u star, then the complement, the vacant set, will not percolate. But what happens at the critical point, what happens when u equal to u star is still open, and it is one of the most important and people generally believe the hardest problem in this area. But in general, the critical behavior of this kind of spatial process are, most of them, they are very hard, as you maybe all know that even for the Bernoulli bound percolation, when on lattice, when d equal to 3 to 9, if I remember correctly, the critical behavior of those very simple model, as simple as Bernoulli bound percolation, then the critical behavior is still open. Okay, but Schneemann also proved that if we look at the range of the infinite version of random interlacement itself, then this thing is with probability 1 always a connected set. So this one is always good and does not have the aforementioned phase transition. Okay, then it is very natural for people to ask if this kind of geometric properties proved known for the infinite random interlacement, if they are still can be inherited by the finite version, by the finitary random interlacement introduced by Louis Bowen. And the first progress toward this direction is also done by Bowen himself. He proved that for a very special class of graphs, that means when this graph is non-amenable, that means the Cheeger constant of this graph is of any finite subgraph of this graph is strictly greater than 0. That means the surface area, the proportion between the surface area versus the volume is strictly bounded above 0. If it is non-amenable, then he can prove for large enough t, then the finitary random interlacement on this non-amenable graph will always have at least one infinite connected component. But he also proposed a question that if the underlying graph is amenable, and especially when the underlying graph is a lattice, it's ZD with d greater than or equal to 3, if whether or not they will have a similar behavior for the finitary random interlacement when we talk about this kind of percolative properties. Okay, so after he proposed this question, and the first several papers, first maybe 1 or 2 papers in in our works, we first concentrate on answering his question, and we do give an affirmative answer to his conjecture, to his question. So we prove something as follows. So first, the first result we prove is for any u and t, then if we look at the finite random interlacement on the lattice, then this random set can almost surely have at most one infinite cluster. So if there is an infinite cluster, then this cluster has to be unique. But this is the first result we prove, and then we prove the following phase transition result. So this means for all u greater than 0, there is always a t1, which is always a finite number. Then for all t greater than t1, then the finitary random interlacement with parameters u and t will have a unique infinite cluster, almost surely. So this is kind of the supercritical phase where we have a huge, actually a unique infinite connected cluster. Okay, and also it has a subcritical phase. This is also proved in our first paper. It is like for all u greater than 0, there's a t0 greater than 0 such that for all t sufficiently small, that means all t less than t0, then the finitary random interlacement will, with probability 1, have no infinite cluster. That means all connected component within this spatial process has to be with probability 1 to be finite. Okay, but there's one remark I want to make at this point. That is because we have already seen that this finite random interlacement has a built-in trade-off mechanism with respect to this average fiber length t. So this means even if we can prove the existence of this t0 here and the t1 here, that means the existence of a supercritical phase and a subcritical phase, it is not immediately clear that we will always have a unique critical value Tc, because the evolution of the system as t increase may not be monotonic. And this is exactly what we prove in this next theorem. For all d greater than 0 and u greater than d greater than 3 and u greater than 0, then the finite random interlacement, if we look at the evolution of this spatial model over all t from 0 to infinity, it is not stochastically monotonistic. And to kind of support this, we also had a number of numerical simulations. And here in this simulation, we calculate the single edge density of this finite random interlacement with multiple t's, but with a fixed u. And we can see the single edge density indeed first increase and then gradually decrease. So this does support our theorem. This is something, well, it is true, this is something that can be rigorously proved, but it can also be supported by indicated by the numerical simulations that this finite random interlacement is not globally stochastically monotone with respect to this fiber length t because of the built-in trade-off property, trade-off mechanism we have discussed before. Okay, but fortunately, although we know this thing is not globally monotonic for all t from 0 all the way to infinity, but if we restrict the range of t to a certain level, for example, if we restrict this t between 0 and 1, then we will be able to still get some kind of monotonicity we want. And with this kind of local monotonicity, we are able to prove the existence of a critical Tc for all sufficiently large u. So here for any d greater than or equal to 3, there is a ud less than infinity. Then for all u greater than ud, then we can always prove there exists a unique critical fiber length T. And for this TC, we can also get its exact asymptotic. So we are able to show this TC is kind of inversely proportional to this U, and we can also get a limit as something like this. And here, this PC of D is the critical value, the critical open probability of a D-dimensional Bernoulli bound population on lattice. Okay, so this result holds for all U big enough for all U sufficiently large. So this is in the high intensity regime. Well, for the low intensity regime, we can also have a number of estimates on the asymptotic behavior, on the limiting behavior of the upper bound and lower bound of all phase transition of this T0 and T1. But in this regime, we are still not yet able to prove that this T0 can equal to T1. We're still not yet able to prove the existence and uniqueness of a critical value. But we are quite close to it, because what we prove is we first we are able to show this T0 and T1, they all happen in the same asymptotic order, at least for D equal to 3 and D greater than or equal to 5. In fact, what we can prove is with D equal to 3, this T0, this lower bound, and this T1, this upper bound, they are all happening at the order of 1 over U squared. And when T greater than or equal to 5, these two things all happens on the order of 1 over U itself. But the only tiny gap happens when D equal to 4. When D equal to 4, we can, if I remember correctly, we can only show that this T0 happens as the order of something like 1 over U times log U. There's a logarithm correction, but for the upper bound, but for the other side, we are not able to somehow be as sharp as with this logarithm correction. We can only show 1 over U, something like that. So there is a gap of a logarithm correction, but we believe this logarithm correction is essential, is a correct one. So we need to somehow strengthen our argument to get the same logarithm correction on the other side. But this is also something we must still work on. Okay, so these are the estimates on the asymptotic behavior of those phase transition in the high intensity region as well as the low intensity one. Okay, but we can also look at the phase transition of this finitary random interlacement from maybe a slightly different viewpoint, a slightly different aspect. That is, if we can fix T and let the intensity U changes, then the question suddenly become much simpler, because unlike T, this finitary random interlacement does not have a trade-off mechanism with respect to U, so we will always have monotonicity. And this approach is proposed by Alex Prevost from Cambridge in 2020, and he has some partial results, and he conjectured that there should be globally a critical value of UC. So because we know that now this finitary random interlacement is monotonic with respect of U, so we only need to show that this UC is globally between strictly greater than 0 and strictly less than infinity. So this is what he conjectured. And this thing is also proved by Zhenghao Cai, my grad student, and myself back in 2021, last year. And we proved this UC T and D for all T greater than 0 and D greater than or equal to 3 is always strictly greater than 0 and strictly less than infinity, which gave a affirmative answer to his conjecture. And according to a more recent result I have with Zhenghao Cai and Iveta Procaccia, we can further show that the phase diagram. That means if we look at this u, c, t, and d for fixed d as a function of t, then we will have a phase diagram in the phase space of u and t. Then we are able to show this phase diagram is always a continuous function with respect to t for all t between 0 and infinity. Okay, so in order to prove this theorem, we need to show that a number of global and local critical values, they are actually equivalent to each other. And this idea is first proposed by, I'm trying to remember his name. Hugo do Coping, I think. I'm trying to remember his name. I'm not sure if I pronounce his name correctly. For the level set of Gaussian free field, maybe in 2020 or late 2019, he proved a similar result for the level set of Gaussian free field, and we found that we can use a similar argument to show the equivalence of a number of local and global critical values for the finite random interlacements, and from that we are able to get the continuity of the phase diagram. Okay, and another aspect of this series of research is to explore some further geometric properties of the infinite cluster of this finitary random interlacement, given such infinite cluster exists, given we are in the supercritical regime. Okay, so the first thing we are interested in is the chemical distance on this infinite cluster. So if we have a connected graph and two vertex x, y belongs to this graph, then the chemical distance or the graphic distance by definition is the length of the shortest path connecting these 2 points. So from this definition, we know that if we have a subgraph of the lattice, then the chemical distance is always larger than or equal to the Euclidean distance on the lattice. Okay, so the important question is if we can prove the chemical distance, which is a larger object, is whether or not it is of the same order as the L2, the Euclidean distance. And this has been proved for maybe first for the simplest Bernoulli bound percolation, the supercritical Bernoulli bound percolation. This thing was proved back in the 90s that the chemical distance, graphic distance, is as the same order as the L2 distance. And for the regular infinite version of random interlacements, this thing was first proved by Procaccia and Sheriff in 2014, but their proof involved a log correction on the upper bound. So it is almost the same order as L2 distance, but still a log correction. And Cernay and Popov in a subsequent paper. So here I need to make a remark that although Aveta Procaccia's paper published on 2014 and Cernay and Popov's paper on 2012, but the archive version, Aveta and his co-author archive it first. So this is an earlier paper and this is a subsequent paper. Okay, and Cernay and Popov, they successfully get rid of this log correction and prove that for random interlacement, the chemical distance is also of the same order as the Euclidean distance. And later, by Dreves, Baladras, and Akim Sapozenikov, they in 2014, also in 2014, they kind of build a general framework to prove this kind of chemical distance estimates for a rather generalized family of stochastic spatial process, including the vacant set, the complement of regular random interlacement, the level set of Gaussian free field, and also include Bernoulli bound percolation and a number of a quite generalized family of processes. And in order to use their framework to prove the estimate on chemical distance, a key ingredient is something called the so-called local uniqueness property. And this local uniqueness property can be seen from a figure here. It intuitively means if we restrict or maybe finitary random interlacement within a finite but large box, then it is possible that we can have multiple large connected clusters within this box, like the red one here and the blue one here. But if we zoom out a little bit and look at the restriction of the same process within a slightly larger box, maybe if here the size of the radius of this box is n, and if we look at a slightly larger box of maybe 1.5n or 2n, then we will be able to say these two large objects, they are actually just parts, just two branches of a larger connected component, a larger connected cluster in this larger box. They will be eventually connected when we zoom out a little bit. So in order to prove this kind of chemical distance estimate, a key ingredient is to prove this local uniqueness property. Okay, so what we did, this is a paper I have with Zhenghao Cai, Xiao Han, Jiayan Ye, and myself in 2020. We finished in 2020, and now it is, we just finished the first round of revision of this paper in Journal of Theoretical Probability as in it back. So, but it is still a preprint. You can find it on arXiv. So we first proved that for the random interlacement, when t gets large enough for all sufficiently large t, then we will, with very, very high probability, have the aforementioned local uniqueness property. Actually, the probability that the local uniqueness property cannot hold is as small as something like this, exponential of a polynomial function. We call this kind of thing a stretchly exponentially small. Okay, so once we have the local uniqueness property hold with a very high probability, then the general framework by Dreves, Balatras, and Sapozenikov will enable us to also have the following estimate on the chemical distance. This will tell us with very high probability, also stretchly exponentially high probability, the chemical distance on the on that unique infinite cluster of a random finitary random interlacement, as when t is also sufficiently large, will be of the same order as here, as the Euclidean distance. So we can also have the similar chemical distance argument to show this is of the same order as Euclidean. Okay, so after the estimate of the chemical distance, and as a direct corollary, we can also prove the following shape theorem that gives the asymptotic shape, the limit shape of a large ball with respect to the chemical distance on this infinite cluster. Yeah, but I would like to also make a remark here that for all these results on our paper finished in 2020, here we will all require this t to be sufficiently large, to be large enough. But recently in 2021, Zhenghao, Aviata, and myself are able to improve this thing slightly to show that this not only holds for all t greater than all t sufficiently enough, but this thing actually holds in all the supercritical regime. So all the local uniqueness and chemical distance estimate and shape theorem, all those kind of things holds as long as it's U greater than UC, as long as we are in the supercritical regime in the phase space. Okay, and also we proved last year that, so we know that we now know that in the supercritical regime, we will have all the good connecting properties, including local uniqueness, chemical distance, shape theorem, all those kind of good things. And we can also have the equivalence of all those critical values. Okay, but we can also show that the phase transition of finite random interlacement is actually sharp. That means we can estimate the decay of those finite clusters in the subcritical regime. So for all d greater than or equal to 3 and all t greater than 0, as long as u is less than uc, that means as long as we are in the subcritical regime of the finite random interlacement, then the probability that any point belongs to a finite cluster of size at least n, which can be written as the same as the probability that 0 is connected to the boundary of a ball of radius n in this finite random interlacement. The probability of this will decrease exponentially with respect to n. So this means with very high probability, with a exponentially decaying probability, we are not able to have any large clusters in the subcritical regime of the finite random interlacement. Okay, so basically this is what we know for now about this model of finite random interlacement. And here I want to use maybe several minutes of my talk to talk a little bit of what we don't know for now and what we really want to prove in the future, the open problems. Okay, so the main open problem, what we really want to know in the future about the finite random interlacement is the existence of a critical fiber length TC. Because now what we know is we have a phase diagram, and this phase diagram is globally non-trivial, and it is globally a continuous curve. We know this, and also we know that the asymptotic of the phase diagram when u goes to 0 and u goes to infinity, this is also something we know. But we want to prove there is, for any u greater than 0, there is a unique TC, unique critical fiber length, such that for all t less than TC, we will have no percolation. And for all t greater than TC, we will have the system percolate, and there is a unique infinite cluster within the finite random interlacement. Okay, so this is also actually equivalent to proving that, because we already know this uc of t is always a continuous function with respect to t. So in order to prove the existence of TC rather than UC, the global existence of TC rather than UC, we not only need to prove this function UC of t is a continuous function, we also need to show this is a monotonically decreasing function with respect to t. Okay, but at this point, we do not have a complete proof of this. And if you can remember or estimate when u is large enough, we are already able to show that for all sufficiently large u, this TC always exists. So our next goal, the next step, we first aim to show that when u goes to 0, we can also have the existence and uniqueness of this TC. And to prove this, because we have already shown the order here at which this phase transition happens. So what we are now aiming to prove is just like what we did for the high intensity region. So although we know that this Finitary interlacement is not monotonically increasing for all t from 0 to infinity, but there's some hope we can show that we do have monotonicity at the correct order we have already found here where the phase transition should take place. So we don't really need to show that this thing is always globally monotonically increasing, which is already proved to be false. But as long as we can show it is monotonically increasing in the order, in the level of interest, we will be able to guarantee the existence of a TC. So this is something we are working on, and at least for the three-dimensional case, for d equal to 3, I think we have recently made some progress. Intuitively speaking, using according to maybe some kind of limiting process to somehow connecting the Finitary interlacement model to a cloud of Brownian sausage or Brownian process or Brownian motions, then we will be able to construct some kind of trade-off between u and t. So because we know the increment of u will always help, this FRI system is always monotonic with respect to u. So if we can somehow find a kind of, in the limiting sense, equivalence between the increment of t and the increment of u, then we will be able to get the monotonicity at the order of interest. This is something we are really trying to prove now, but maybe a further question, and we believe it should be a much more difficult question, is to show what happens when t equal to tc, if this tc really exists. But we assume it can be a very, very hard question because we know that this FRI, this Finitary interlacement, is kind of a bridge between one side is the regular infinite random interlacement, and the other side is the classic Bernoulli bound correlation. But for both sides, for both limits, the critical behavior at t equal to, at this u equal to uc or p equal to pc, the critical behavior is something very, very hard, and even many of those problems are still open. So this means if we want to look at the bridge between them, then what happens when t equal to tc, we believe it should be a very hard problem. But we also did a number of this kind of numerical simulations, and all the numerical simulations seems to indicate that the phase diagram is monotonic and there is a unique phase transition. And here, this is a histogram of the size of the volume and also the diameter of the largest component for different u and t within a large box. And you can see the phase transition is really, really rather sharp, and it seems like the phase diagram is monotonic. And here, this is an estimated, simulated phase diagram like this, according to a hill climbing algorithm. And we can see seems to be monotonic, the phase diagram, but we are still trying to prove it. Okay, and another thing we are trying to prove is we want to get some more precise, even more exact estimate on the asymptotic behavior of the critical value of the phase diagram. We have already shown that maybe when d equal to 3 or d equal to 5, this UC is when d equal to 3, this UC is inversely proportional to t squared. And when d equal to 5, this UC is inversely proportional to 1 over t. But we also want to show it's not just like an upper bound and lower bound. There should be a limit like C3, C4, and CD greater than or equal to 5. But for this one, we also have some progress in the case of d equal to 3 using the connection between properly rescaled, this kind of finitary random interlacement, and the cloud of Brownian sausage. And by the way, for this kind of pass-on-point process induced by a cloud of Brownian sausage, a very similar model was introduced by Erhard, and I think he's now in Brazil or something. Well, but back then, I think when he proposed this model, he was in Warwick, UK. And so if we can build some connection between our model and a certain variant of his system, then I believe we have more hope to first prove equation 5, to first prove a more exact limit for d equal to 3, but how to do it, how to push it up to d equal to 4, this is something we're still thinking about. Okay, so in the end, we have a list of works related to this talk, and let's see, and that's it. And thank you so much. Thank you.
Okay, thank you very much for the interesting talk. Questions, comments?
Yeah.
Yes, I have what's probably a stupid question, but is there any way? is there any way of tinkering with the way the trade-off happens to make it monotonic in T? So instead of dividing by T plus 1, can you divide by something which is slightly different?
Oh, yes, that is a very good question. So this involves why we need to have this T plus 1 in the denominator. So basically, the reason we want to have a T plus 1 here is because of in the definition of a geometrically truncated capacity of a certain site with respect to a geometrically scaled random walk, then we need to have this in order to make sure that for any given site, given fixed finite site A, then under this setting, the number of trajectories traversing this finite site, the expectation of this is always proportional to the truncated capacity of this finite site A. So, the main motivation, the main reason that we need to put a T plus 1 here is only with this T plus 1 we can have, as T goes to infinity, the finitary random interlacement can converge to the regular infinite random interlacement. So I believe this is the main motivation that when Bowen was defining this finite random interlacement, because he wanted to make this a finite version of the infinite random interlacement, which was introduced first. So he need to have this scaling factor on the denominator to make this thing converge to the infinite model as T goes to infinity.
But that is an asymptotic statement, but the monotonicity is sort of finite T. And maybe you could play around with it so that asymptotically it was the same, but for finite T it was a bit different.
Oh, yes, I think that is a very good point. So maybe here, let me think about it. Unfortunately, maybe the answer is no, because I mean, in order to have this asymptotic behavior, then we will always need the denominator to be of order of linear T on the denominator.
Sure.
But according to our proof of this non-monotonicity, actually, if we look at the details in the proof, I believe the only thing we use is this function is of a linear order as T go to infinity. Then we will, as long as we have this, then we will have a decreasing tail like what we have here. So it seems like we can not do much thing to retrieve monotonicity with somehow playing with the denominator, but that is a very good idea.
But it doesn't. Thank you.
Any other questions?
Yeah, could you say anything about the like the motivation to study this model, other than this other person kind of brought it up? I mean, what are we sort of learning here about ZD or something? I don't know.
Okay, yes, thank you. That's also a very good question. So I think for me personally, I think the main motivation of learning this thing is this finite random interlacement is really a good connection, a natural connection between the two very famous, very important models. The first one is, let's look at here. If we let u go to infinity, t go to 0, well, at the same time, u times t remains a constant, then on this limit, this finite random interlacement will converge to the Bernoulli bound percolation, which is a really classic model in the field. And also, as Bowen proved, if we fix u as t go to infinity, then this model will converge to the regular infinite random interlacement. But as we can see, these two models, they are really very different from each other, because we know the Bernoulli bound percolation is actually the open or close of every edge is actually independent to each other. But for the infinite random interlacement, this thing is actually a model to have long correlation. Actually, the correlation in the regular random interlacement will decay polynomially, so it really decays really slow. So on the two ends, these two models, they behave really differently. So another motivation is because this finite interlacement is somehow a connection between them, and we already prove in the high intensity regime the critical behavior, the asymptotic behavior of the critical value of the finite random interlacement is really highly dependent on the critical value, the critical probability of the Bernoulli percolation. Well, on the other side, it will behave really similar, especially in the proof. We can see the geometric properties of this finite random interlacement is really similar to the infinite regular random interlacement model with long correlation. So another very interesting thing we want to further explore is how this kind of long range correlation decay, and how the model somehow evolve from this more random interlacement thing to a more Bernoulli percolative thing. So this is also something interesting. And another motivation of this is actually Alex Prevost from Cambridge. He shows an interesting connection between the finite random interlacement and the massive Gaussian free field. He shows some isomorphism between these two models. And also recently we find that maybe we can use some estimate on the massive Gaussian free field to somehow help us prove those more exact asymptotic behaviors of the phase diagram of FRI. So this is also something we find maybe interesting. We want to motivate us to further study this model. Thank you.
Yeah, no, thank you.
Yeah. Any other questions? Okay, if no other questions, I'll ask one question. Slide 18.
Slide 18, sure.
Yes, 18. So I would like to understand how much information, say for the two numerators, let's say put d equals 3. For the two numerators, how much is the gap between the two?
How much is, let me see if I can.
Well, yes, they're both of the order of log u. And then let's say if the numerator is how much difference between the two?
Yes.
Do we have
when
any
you,
information of this?
Yes, exactly. So for d equal to 3, actually we can prove something slightly stronger than this one. Actually, what we can prove is something like this: t0 is maybe greater than or equal to c times u negative 2, and t1 less than or equal to maybe another capital C of u negative 2. So we can show, yes, so we can show something a little bit stronger than this, and also
still,
for d equal,
yeah.
Yes, please.
Yeah, with the difference, you don't know.
Yes, but the exact value of this small lowercase c and this capital C, well, we can have a, now we can have explicit expression of this lowercase c and capital C, but for now we are not able to show these two C's, they are the same. So actually, what you are asking is what we want to prove here. So here we actually want to prove this lowercase c and this uppercase c, they are the same, and they will convert to the same C3. But I think for at least for d equal to 3, we have some idea of how to proving this, and my grad student Jing Hao, he's trying to writing down his idea and trying to finish the proof of this, but we will see. Thank you.
Okay, thank you very much. Okay, are there other questions, comments? Okay, if no questions, comments, let's thank Yuan for the interesting talk again. Thank you.
Yeah, thank you. Thank you.
All right. Tomorrow is a Good Friday, and happy Easter to all of you, and see you in the next talk. Bye-bye.
Yeah, thank you, Professor Xia,
Thank you.
and
Okay,
thank you everyone for your,
okay, bye-bye.
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 Bye-bye.